All right, taking a look at example 4, we have two posts. One is 12 feet high over here on the left. The other one is 28 feet high, and they are 30 feet apart. They are to be steadied by two wires attached at a single stake that's running from the ground level to the top of each post. Where should we place the stake to use the least amount of wire? So we, once again, want to be minimizing our distance here. Now, this distance down at the bottom is essentially just the length of the wire. Now, the wire is made up of this formula, right? Y plus Z, where Y and Z are the distance created by the wire here, attaching the post to the ground, the stake in the ground. And we're allowed to move the stake wherever we want along this spot. So we have to keep that in mind. Now, since we know that it's 30 feet, whatever we call this distance for this triangle X, this distance over here is going to be 30 feet minus that amount. So if we pick 5, right, 30 minus 5 is 25. That's kind of the ideal setup here. So our equation, our primary equation for this problem is really this length of the wire we're going to call W, okay, which is equal to Y plus Z. And our secondary equations, and we say equations because we're going to have two of them, is how do we figure out what y is? Well, in order to figure out y, we have to use Pythagorean theorem, right? So y squared is equal to x squared plus 12 squared. All right? And at the same time, z squared is equal to that 30 minus x squared plus 28 squared. Okay, so if we look at this first equation, we can figure out what y is just by taking the square root of both sides. So y is going to equal the square root of x squared plus 144. All right, and likewise, z is going to equal the square root of this 30 minus x squared, and we'll just leave this as plus 28 squared because that's going to be just a big number that I don't want to, it's easier to write down this 28 squared. Okay, so my primary formula is W equals, all right, and notice that both now y and z are just in terms of x. So remember, we want to get our formula in terms of one variable. So the square root of x squared plus 144, all right, and then plus the square root of 30 minus x squared plus 28 squared. Okay, recall for our purposes that the derivative of the square root of x is 1 over 2 square root of x. If you want to think about this as being a u instead, okay, the square root of u, or u to the 1/2, it's going to be u prime over 2 square root of u. So this formula is what we're going to be using to find these derivatives. All right? Now, we can do this without actually taking the derivative, but if we needed to, right, we could say that w prime is going to equal, we're going to get 2 times this square root, and then this, right, is going to be the derivative of what's inside, is u prime, and the derivative of what's inside is just 2x. All right, and then likewise, the 2's are going to drop out, so I really just get x over the square root of x squared plus 144. And on this side, I get the same thing. So 2 times the square root on the bottom of 30 minus x squared plus 28 squared. All right, and we take this, the derivative of the chain rule. So once again, the derivative of what's inside. The derivative of 28 squared is just 28. And the derivative of this is going to be essentially just negative 1, because that's the derivative of what's inside this. It's like a double chain rule. So the derivative of what's inside is just this 30 minus x to the first times the derivative of this 30 minus x, which is negative 1. So that's where this negative 1 times this is going to come from. So we can really think about this as just being x minus 30. When we multiply by negative 1, the signs are just going to change. Okay? There's our derivative. So worst case scenario, that's all we have to do. All right? Now, what we're going to do for this question is we are not going to be able to easily figure out when this is equal to 0, okay, or undefined, because we have two different values. So keep this in mind, that this is going to be a calculator question, okay? So the first thing we're going to do is we're going to create our equation, our function. We're going to call it w of x, and we're going to let w of x be the derivative of that function. So the first thing we're going to do is we're going to set w of x, okay, equal to, so control and then symbols, and we know that we're using that square root function, and I'm typing in the original equation here, this guy, square root of x squared plus 144 plus this, okay? So x squared plus 144, and then plus, and we have the square root of, and then same thing, here we have 30 minus x squared plus 28 squared. All right, and we're got done. We'll double check to make sure that's the same, and we're good to go. Now, we're going to let this derivative, and we can call it whatever we want. We'll call it, v if you want, okay? V of x is going to be, we're going to do control store, so our store function, okay, control symbols. And this time we're going to press, remember the shortcut for the derivative button is shift, I think it's plus. Nope, that's integral. So shift minus, control Z to undo. Okay, so we're going to do d dx, and here we're going to put in w of x, and it says we store the derivative, okay? We don't know what the derivative is per se, like the calculator's not going to tell us what this equals. If we try to type that in, shift, okay, and we put w of x here, the calculator says we can't do that, okay? So you just got to be careful. It won't actually spit out the derivative for us, so just be aware. All right? Now, if we're going to maximize this, all we want to know is when does this derivative, this function, v of x, we want to know when does that equal 0, okay? So notice that we've called this function v of x, all right? So we want to know when is v of x equal to 0. And then we want to know when is v of x essentially undefined. Now, because these square roots have a squared in them, that's never going to equal 0 here. And because we have a quantity squared plus 28 squared here, this is also never going to be undefined, okay? Because this quantity is always going to be positive, and we're adding 28, and if 0 in, becomes 28 squared. So it's never going to be undefined. We don't have to worry about this part of it. And instead of putting this little symbol here, we're going to put undefined, and we don't have to worry about this, okay? All right, so now, when is it equal to 0? We're going to set v of x equal to 0, and we're going to solve. So on our calculator, we're going to go menu, algebra, and solve, okay? We're going to say v of x equal 0, and we're solving for 0, and we're solving for x. And we get an answer of 9, okay? So that is when, all right, that is when the minimum or maximum number could occur. That's our point here. Now, what we can do is we can also check to see if it happens on the other side of 9. So remember, we're going to choose given. We're going to say x is less than 9, okay? And notice we're getting an error here. because there's an accuracy question. This is essentially 9. It doesn't happen again. Or we can check to see if it happens on the other side of 9. And then same thing. It's spitting out some really number that's super close to 9, and it's giving us this little error message because there's a little bit of accuracy. So it doesn't happen anywhere else. It's just happening at 9. Okay? So just keep that in mind. All right. Now, we know that it's happening at 9. We want to check what's going on around 9. Because remember, if we're using our first derivative test, okay, our first derivative test, we know that this is 9. We want to check something to the other side of 9 over here. What's happening, let's say, at 0. And then what's happening over here, let's say, at 10. So we can just do the derivative, v of 9, right, we know is 0. V of, let's say, 0 is negative, and v of 10 is positive. So we know that we are negative to the left of 9 and positive to the right of 9. So we definitely have a minimum value here, okay? And now we also know that we can figure out specifically that since x is 9, this is this distance from here to here. So we know that this is 9, okay? And if we plug 9 in for x, 30 minus 9 becomes 21. That's how far away from the poles. So where should the stake be placed to use the least amount of wire? Okay? And then, nice and easy, we can state our answer. The stake should be placed 9 feet from the 12-foot pole and 28 feet. Sorry, 21 feet from the 28-foot pole. All right, and that's it. So thanks for sticking along. Hopefully it makes sense how we're using the CX here to store the original function, and then create a function for the derivative, and then we can evaluate that derivative and solve for critical points using nsolve here. All right, hope you guys have a great rest of your day.